Okay, so far we've seen fully connected networks like the multi-layer perceptron. We've seen how the convolution works. Now we want to compare because CNN have been so popular. So we want to see what are the advantages that CNN have compared to fully connected networks. And CNN have three important properties which allowed them to improve the performance of a lot of many machine learning systems. And these properties are sparse interaction. This is also called sparse connectivity, local connectivity, or sparse weights, parameter sharing, and translation equivariance. So this is, let's compare the fully connected network versus the convolution network. So you can see here that for a fully connected network, you have dense connection, like every input, this input is connected to all the other, this output, sorry, is connected to all these inputs to X1 till X5. As you can see here, these are all the connection of that. And the same thing for O4, it is connected to all the inputs, X1 to X5, and that's why we say it's fully connected, or it has dense connections, as opposed to the case of a convolution kernel. So this output here is only connected to three inputs, because you have a kernel. If you remember, we had a 3x3 kernel, for example. So these connections are sparse as opposed to these ones which are dense. And so if you have a fully connected network and you have M inputs, like M pixels here in a layer, and N outputs in the next layer. So this requires a computation of M by N parameters. For example, if you have a 1000 by 1000 image, 1000 pixels by 1000 pixels, and you have 10 to the power 6 hidden units. So you would require 10 to the power 6 multiplied by 10 to the power 6, which is about 10 to the power 12 parameters, 10 to the 12 parameter weights that you would need to determine. Okay, as opposed to the case where you have a kernel. Now your input K is much smaller than M. So you require only K by N runtime per example or per image. So K is typically several orders of magnitude smaller than M. For example, if you have the same case, 1000 pixel by 1000 pixel image, and you have 10 to the power 6 hidden units, and you have a filter size of 3 by 3, then you only require 10 to the power 6 here multiplied by 3 by 3, which is almost 10. So it's 10 to the power, almost 10 to the power 7 parameters. 10 to the power 7 parameters that you would need to determine only. So this is also, well, let's look at the growing receptive field. So these sparse connections are kind of important. So although these connections are very sparse, deeper layers are indirectly connected to most of the input image. So for example, let's say you have your input layer, your hidden layer, your output layer, and you look at this output here. So you have sparse connections, true, because you're connected only to this kernel here, but then each of the hidden layer is connected to the other ones. So this output actually, which is, if you're assuming that you have a large number of hidden units, so this input here has this receptive field, but actually it is connected to a much bigger receptive field. So receptive fields of units in deeper layer, for example, the output layer, is larger than the shallow layers. And that's why you know, when you have your input image, the first layers would extract basic features like this edge, this edge, this edge, and so on. So it will extract edges. And then for faces, for the case of faces, it will, the deeper layers or hidden layers would extract an eye, an ear, and so on. And then these features are put together to recognize a person. The same thing for cars, for example. You have the same thing. The first layers are always used to, or their function is always to extract these small features like lines and so on. And then the deeper layers or hidden layers, deeper hidden layers would extract, for example, a door, a window, and so on. And that would allow you at the end to distinguish between the different type of cars. The second property which makes the convolutional networks attractive is this parameter sharing. So for example, for a fully connected layer, you have a traditional matrix multiplication and you do not share any parameters. For example, this node here would have these parameters, okay? That's why they're colored differently. And they're also different color from the nodes or the weights of between this output node and the input nodes, and the same thing for the others. So there's no parameter sharing, no same weights. The weights are not the same. As opposed to the convolution, the case of the convolution, when you have an output here, you have a kernel. So the parameters of the kernels are shared. So you just determine the parameters or the weight of this kernel. So this same kernel is used to you convolve with this output is the result of the convolution. So you have only 3 parameters here. The same thing for this one. It has the same weights, and that's why they're colored the same way. So this has this parameter sharing also helps in the computational cost, of course. Fully connected traditional layer networks, if you have an M inputs in a layer and N outputs in the next layer. So here, for example, this is your input image. You have M inputs or M pixels in total, and you have N outputs in the next layer. So this requires M by N parameters, as we've seen before. Now, if you're doing this, or you accomplish by making kernels smaller than the input, so if the size of your kernel is K, so let's see maybe an example to make it clearer. So if you have, again, 1000 by 1000 image, 1000 pixel by 1000 pixels, and you have 10 to the power 6 hidden units, and you have a filter size of size 3 by 3. So this would allow you to get only 9 parameters here. And this is much cheaper compared to the previous case. The third property which makes convolutional neural networks attractive or more powerful than the fully connected layers is this, translation equivariance. So if you have 2 functions, for example, f of x, you say that this function is equivariant to a function, another function g, if you apply g to a certain input, and then the result is applied to the second function. It's the same thing as if you do the opposite. For example, if you have an object and you rotate it, that's the first function, and then you translate it. It's the same thing as if you take that input image, that input object, and then you translate it and then you rotate it. So they're equivariant. These translation and rotation, you can say that they're equivariant functions. For our case, for the convolution, This parameter sharing causes equivalence to translation. So convolution is equivalent to translation. It allows the features to be detected regardless of their position in the visual field. So if you have, for example, an edge, as we've seen the example before, this edge would be detected the same way regardless of where it is in the receptive field, wherever it is in the image, okay? And all neurons in the first hidden layer detect exactly the same features, just at different locations. These are the three properties which makes convolutional neural networks attractive. Thank you.